All right, so now we can get started. So thank you everyone for coming. Some of you might have had your mind in the gutter with the title of the talk, but it's nothing like that. It's about the macro and the nano world. So I'm here to talk to you about magnetism and how it manifests itself in your daily lives and how we use it as a way of generating electricity. And I'll talk about other applications as well. And when we get to the nano world, I will give you a little taste of the kind of research that I do. So welcome. All right. So everybody has had experience with magnetism. We've all played, I'm pretty sure we all played with Wooly Willy up here and made fun faces like here and in the background. And then I found an antique website, a female version of Wooly Willy named Betty Burnett. So, you can not only make facial hair for men, you can also do ladies' do's. And sadly nowadays people are moving toward the stainless steel appliances and they're not decorating the fridges anymore. If you come to my apartment, my fridge is loaded with magnets. Now that's not my fridge, I stole that from somebody online. But yeah, you come to my place and my fridge is just full of magnets, everyone's children, all my friends send me Christmas cards. I don't throw them away. But yeah, so this is how magnetism has influenced you as children and even into your adulthood. Now, let's figure out what is magnets. It all started in ancient civilization where magnetism was first discovered with lodestones. And these are just naturalized, magnetized pieces of magnetite which could attract iron. So our ancient ancestors, were well familiar with magnetism. It was this invisible type of force, and they didn't really understand what it was. We're still trying to understand it at a more fundamental level in physics. But here you can see a picture of magnetite, and it is attracting staples. Now, for more than 800 years, sailors were using magnets made of lodestone or treated iron to navigate the globe. And here's a picture of magnetite, our lodestone, behaving like a compass needle. This is a very simple compass that we're all going to build at your tables, and it's going to involve a very strong magnet. It's going to involve a paper clip, and probably the water that you all knocked loose and got your tables all wet.
Fill the dish up with beer.
Renee, like I told my students today, that's a waste of beer. Not wasted. What they said was, well, the part of the rock that pointed north is called the North Sinking Pole, or simply the North Pole. And in the 1600s, William Gerber suggested that the compass works the way it does because the Earth is a giant lodestone. It itself is a giant magnet. And that's what's shown in this picture here. What we have is we have the Earth. This is the rotational axis of the Earth. And this is the geomagnetic North Pole. And this is the geomagnetic South Pole. Notice that the south end of the magnet is taking, pointing in geomagnetic north. That is because, by definition, we're defining the north pole of the magnet to point in the geographic north. North poles are attracted to south poles when it comes to magnetism. So, let's have some fun. So, what I have at your tables is a paper clip. Now, I don't have enough for everybody. Well, I kind of did, but. So what you got to do, and our clever physics major back there made this discovery in lab, what you gotta do is take your paper clip, take one end and have it point straight up, like so. Alright? Yeah. And the reason why you're doing this is because you don't want to break the surface tension of the water. You don't want to touch the water. You just want the paper clip to touch the top of the water. But don't put in the water yet. Who did it?
I did.
Oh, yeah, we got to magnetize this thing. All right. Now what I'm going to do is I'm going to visit each table, and I am going to bring a very strong magnet. All you are going to do is take your paper clip and hold it there for maybe a few seconds. Well, let me put this outside. And don't do anything with it. No, that's fine. What that paper clip did was it experienced a force from the Earth's magnetic field and caused your paper clip to rotate, okay, and orientate itself in a direction, which I think this end was north. So it should have pointed north, or directed toward north. All right. Yes. Well, that I don't know how long it is. I mean, it'll stay, I mean, if you drop it several times, I know. Okay. So, was that cool? Yeah? All right, let's move on. So now comes the question of size. So, when you look at the Earth is huge. The Earth has a radius of about 6 million meters, which means that it's about 3,958 miles in radius. Okay? If you look at how strong the Earth's magnetic field is, it's of the order of 0.0305 millitesla. So so all of you have measured with the ruler before on a centimeter scale. And, yes, Rahul?
I just wanted to say I did.
What's that?
He did measure. Yeah, he did.
Oh, you did measure. All right, good for you. Good for you. So on the centimeter side of on the ruler, you have little divisions that are millimeters. Some of our students have a hard time with millimeter. So, that's quite small. That's a very small number, magnetic field. Okay? Think about it. You have the entire size of the Earth, and it's creating such a weak magnetic field. How weak? Well, let's look at our lodestone. A lodestone is roughly 1 to 2 inches, and the magnetic field strength is about 10 to 30 milliteslas.
Wow.
So what you see here, it's not the actual physical dimensions of the object, but what matters is the strength of the magnetic field. Okay? So that is my talk. Thank you for coming. I'm just kidding. So I found this cute video from my biologist friends, and not only do paper clips want to align with the magnetic field when it's magnetized, but animals have a sixth sense. And this is a really cool video about magnetoreception.
Imagine waking up on the beach before dawn. The glimmer of light leads you to the shoreline. Suddenly, a wave pulls you in. At first, you use the direction of the waves to guide you. But once you're in the open sea, with powerful currents bombarding you and very little light, how can you be sure of where you are and where you're going? For a hatchling sea turtle, the answer is magnetoreception. That's the ability to sense magnetic fields. We know many animals use this sixth sense for navigation. What we don't know is exactly how magnetoreception works. Here's what we do know. Earth itself is like a giant magnet. The motion from its liquid outer core generates a magnetic field. Certain animals can sense this field and use it as a compass to tell them if they're heading in the right direction, and a map to give them signposts along the way.
There's two competing theories for how magnetoreception works. One is a chemical sensor, and the other is a mechanical sensor.
The first theory is that animals have tiny magnetite particles in their bodies that act as magnetic receptors. Magnetite is the most magnetic natural metal on Earth. It's been found in many animals that exhibit magnetoreception.
And it's thought that it's the only potential sensor that would be sensitive enough to capture these incredibly tiny variations in magnetic field strength that would allow the animal to not just know whether they're going north or south along the magnetic field line, but know the precise beach that they need to get to.
The other theory is that animals possess a protein in their eyes called cryptochrome, which allows them to see magnetic fields. Cryptochrome has been found in the eyes of several migratory birds, but we haven't proven either theory for a few reasons.
With magnetoreception, you don't know where to look. Magnetic fields pass invisibly through the entire body, so researchers don't know exactly where these magnetic particles or cryptochromes would be attached to particular cells, and so mistakes are made all the time.
And so far, cryptochrome experiments have only yielded positive results in the presence of magnetic fields much stronger than Earth's.
The frontier is now not so much at the animal behavior level, but actually getting inside the brains of these animals and trying to find these sensing cells and connecting them to the neural circuitry. It's not so much a question of which animals have this sense, but which don't. So researchers have said, well, why not humans? Maybe we had this sense at one point deep in our evolutionary past and lost it. Or maybe there's a vestige left. Researchers in California and Japan have gone after this holy grail one more time with a very specialized experiment, one that relies on double blinding and magnetic shielding, and they're seeing glimmers, maybe even more than glimmers, of this magnetic sense in humans. It's starting to be reproducible, and they're really excited about it.
Yeah, so these animals and my biology friends probably know more about it than me because I've never taken a biology course since freshman year of high school, so that was a new thing for me to learn. So, biology friends, do you have anything to add? Sean, Caitlin, Gary? Really? Well, you learn something new every day. Well, up front. All right, so now what I want to do is I want to spend some time talking about the properties of magnets. What is very important is that magnets is not the same thing as electricity. We're going to see pretty soon that there is a relationship between electricity and magnetism, but magnetism and electricity are not the same thing. So what do we mean by that? You have a balloon, and you rub your head with the balloon. What does your hair do? It goes up, right? A magnet is not going to do that, right? These are two different forces, but we're going to see that there is a relationship between them. Magnetism is a long-range force. As an example, I have a very strong magnet here. I have a compass needle over here. And you see that this compass, there's no actual touching between the compass and the magnet. So the force acts over a distance. Materials that are attracted to magnetic are called magnetic materials. And when you look at a magnet has two types of poles. A magnet has a north pole and it has a south pole. And what some of you have on your tables, and you're going to have to share it between the different tables, is I have a, oh, that's okay. I have a piece of plastic with iron present. And what you're going to do is you're going to take the magnet on the table, thank you, and you are just going to place the piece of plastic over the magnet, and you'll be able to see the magnetic field.
Do you see it? Do you see the pattern?
South pole and attracts the north pole must be the magnetic field. So in this picture here, what I'm showing is a north part of the magnet and a south part of the magnet, and you can see that there is a attraction between the two poles. If they are the same pole, north and north, the magnetic field lines don't want to crunch together. Well, they don't want to, they fill in this gap here, and then you see that they repel one another. The lines of force are preventing them from coming together. So this is a nice picture. And if you want, you can meet up with other tables later on and bring the magnet at your table to a magnet at the other table and feel the attractive and repulsive force between the two magnets that you used in the previous demonstration. Now, this is very fundamental. If you were to break a magnet in half, the result is two weaker magnets. And what that means is that the basic unit for magnetism is what we call a magnetic dipole. That means there's two poles, a north and a south pole. As far as we know, we cannot isolate a magnetic north and a magnetic south separately. They come together in existence. There's theories out there that these magnetic monopoles do exist, but they have not yet been observed in nature. And because they were not observed in nature, I don't know if they exist. Okay? So, you can't break north and south. Yes?
So I know your thing is nano,
Yeah.
so it doesn't matter how small it is.
It's still going to be a dipole. Yeah, there's no
They've done
particle.
that research on it.
Well, we're still looking for that. Yeah, it's still a current research problem, is we're trying to find a single magnetic north and a single magnetic south. And we call that a magnetic monopole. So right now, you know, it hasn't been, to my knowledge, it hasn't been observed. So therefore, we don't know if it exists. Right now it's theoretical. Yeah. Which is okay. So some of you are probably curious on how to make a magnet. And it's very simple, but I would not do this at home. This is illustration from Gilbert's book, De Magnetite. And what you see here is a blacksmith pounding a piece of metal. So what you do is you heat up an iron bar so that it looks red hot. And then you start beating it with a hammer. Okay? And then what you do is you align that iron bar with the the north-south direction of Earth. So that way, one end of the piece of iron becomes magnetic north, and the other one becomes magnetic south. And then what you do is you're going to let the iron bar cool in that position. And then you have a magnetized iron bar. And you can verify this by bringing a magnetic object near the iron bar, and you will find it will be an attractive tendency for that magnetic body to gravitate toward your iron bar.
Why is it making a magnet? Why does just...
Well, iron, well, okay, we're gonna get there. We're gonna be talking about atoms.
Oh, great.
So iron, okay, we're gonna be getting here. Okay, so, what's that?
Just one atom. Thank God.
You are sitting, Kayla, you are sitting way close to Patrick. Okay?
There's some kind of force.
Yeah,
What's it called?
They're called conference. Okay, so, Christine, we will get there later on.
Okay, I'm ready.
Okay? But just accept that that piece of iron bar becomes magnetic. Okay? So, now what I'm going to do is... Okay, that wasn't supposed to stop. Okay, so let me tell you what's going to happen. I am going to show everybody that using electricity, you can make a magnet. And that's what we call an electromagnet. Now the way how this works is I am just going to use some batteries, right? And we all know that when you connect a battery to a light bulb, what happens?
Lights up.
The light goes on. You create electricity, right? So let me just demonstrate that for you. Well, thank you, Renee.
That's what you just said.
Is it gonna blow up in my hand?
Yes.
Right.
I'm not Scott.
Can you jump start my car?
That was probably nothing new to anyone in this
Yeah.
room.
Wasn't lightning.
Now, the next thing we're going to do is I am going to use this coil. And I'm going to connect the coil to the battery. And I'm also going to need a volunteer to hold this compass needle. So I need me and two other people. Renee? Anyone else? Gary, you want to help? Okay, you're going to hold the compass needle, and you're going to stay far away for a little bit. Okay? Renee, we're going to connect this coil to the battery. And I'm going to electrocute myself.
We got paperwork to do if you want to keep yourself.
Alright, hold that up. Hold that up, Carrie. Get close to the magnet.
Oh, it's moving.
Which way does it point? Pointing toward. So go far away. Now come closer. You see that? So what you've done is you used electricity to create magnetism. This was discovered in, I believe, the mid-1800s, and I have a nice little video that shows you what is happening there. So let's watch it. I put these videos here so I can just drink more beer.
We know, you're so smart.
No.
In 1820, Danish physicist and chemist Hans Christian Ørsted was setting up materials for a lecture. These materials included an early kind of battery called a voltaic pile, constructed of copper and zinc plates in a dilute acid solution and a wire held in place here by a set of clamps. the convention is to think of electrical currents as moving from positive to negative. So that's how we'll show it here, using red particles. Back then, scientists still had much to learn about electricity. Preparing for his lecture, Ørsted made a very important discovery about the phenomenon, quite accidentally. Among Ørsted's scientific paraphernalia was a compass. Its needle, of course, pointed north in alignment with the Earth's magnetic field. Ørsted happened to place the compass near his battery and was startled to notice that the compass needle moved. As Ørsted deduced, this happened because the wire produced a magnetic field around it when it carried a current. If there is no current in the wire, the needle reverts to the alignment with the Earth's magnetic field. As it turns out, an electric current, made up of moving charged particles, produces a magnetic field that circles around the moving current, as shown by these blue lines. If you reverse the direction of the current, then the magnetic field around the wire moves in the opposite direction, and the needle on the compass flips to reflect the change in field. If you move the compass to a new spot near the wire, the needle will realign with the direction of the magnetic field in that particular location. Ørsted's accidental discovery was solid evidence that electricity and magnetism were related phenomena. The announcement of his findings incited a tremendous outbreak of research in the nascent field of electromagnetics in the early 1820s.
So that video is nice because it shows you animation of what's going on there. And I didn't have to spend a great deal amount of time reviewing what electricity is and all that other fun stuff. All right, so things get a little bit more fascinating. So right now, we see that you can use electricity to create magnetism. Now, the next thing is probably one of my most favorite things in electromagnetism. In the mid-1800s, Michael Faraday and Joseph Henry in the US, Faraday was in England, were able to generate electric currents without the need of a battery. What he did, just to make it very simple, is if you have a magnet, like I showed here, and if you have a wire, like so, if there is relative motion between the magnet and the wire, you can generate electricity. Okay? I will show you why this happens shortly, but I'm going to show you that it does work. So what I have here is I have my coil, and I have my very strong magnet. Connected to this coil are LEDs. I have a red LED, and I think a yellow or orange LED. Probably yellow or orange, I don't remember. I've done this so many times, I don't remember. Now, what's nice about LEDs is if the current flows in one direction, it will light up. Okay? So, the current's going to flow in one direction and cause it to light up. That's important. So, I'm going to put the north pole of this magnet through the coil. And you're going to tell me what you saw. Renee, can you hold this up, please?
Lower so it's not against the.
Yeah, the white screen.
Hold it lower so
There you go.
so it against the line.
Yeah, good.
Oh, that's good.
There we go, ready? Wow. Yellow lights up, did you see that?
I did.
There again. Wait, going in, yellow lights up, pulling out, red lit up. So, what we did was we created electricity. And all you need is the relative motion between the magnet and my coil. Now, this has some very important applications because this is how a generator works to create electricity. And to demonstrate this, I brought with me a wind turbine. So we just got this in the physics department for my alternative energy course. I built it today, but let me just show you what it has. Oh, not yet, Renee, but pretty soon. Thank you. No, you're Hannah. Okay, so what the base has inside this black circle is a smaller version of this coil. Okay? And what's at the bottom of this wind turbine are magnets. You can see them right here. Does everybody see them? Yeah. All right. This was a pain in the butt to make, only because they put some sticky tape on the back of these magnets, and I don't have nails, and I couldn't get it off, so, all right. Oh, it's okay. Oh, it's okay, we're just gonna rebuild it. It's real quick. It's designed to do this. Oh yeah. Yeah, this is a is there any electricity flowing? No. All right, well let's make some electricity. And what I brought with me is a fan that was donated to our department by Dr. Kiefer. It's very sophisticated, from the Walmart. Thank you, Jerry. And Carrie, I might need your help too. All right, you're gonna hold the fan. I'm gonna hold the wind turbine.
And I'm gonna hold the LEDs.
Yes, and I'll tell you when to turn the fan on, okay? So we're gonna hold this straight up, and at first we're gonna raise it really high in here. So we gotta get the flow, so raise it higher. All right, there we go.
Whoa.
Is it lighting up?
There we go.
Is that cool? So for the people in Zoom, can you see it? Awesome. And that fan feels amazing. For there to be electricity being generated. And essentially what's happening is when there is a change in the number of magnetic field lines going through this area, the electrons in the conductor are going to respond to that change. They don't want that magnetic field or that magnetic flux to change. So what they do is they move around in such a way to cancel out those increasing magnetic field lines. And that is how electricity is being generated. Now, I could demonstrate this with the magnet and a copper tube, okay? Now, if I were to drop a paper clip through this copper tube, pay very close attention how long it takes for it to fall. Ready? One, I'm gonna drop it. 1, 2, 3. That was quick, right? Now I'm gonna take this magnet and I'm gonna drop it through this copper tube. Remember, copper is a conductor of electricity. It's got electrons moving around in random directions. And when I introduce a magnet, these electrons do not want these magnetic field lines causing any change. So they're gonna swirl around to counteract that change. So if it's counteracting that change, what type of force is it gonna be? Is it gonna push it down or push it out? Push it, I wanna push it up, right? So it should take the magnet a longer time to fall down. Are you ready? Oh, it's really taking its time. Oh no, you know what? I gotta take the. Okay, technical difficulty. They got these little, they got these little things. Let's see. All right, here we go. Ready? Let's try it again. You saw it took longer, right? Later on, if you want to see what's going on to the top, you can watch it as it falls. And it's really cool. It's like It's just like a feather. You know, wobbling its way down the tube. All right, it's a very simple experiment. I could pass this around if you want. You can try it. All right. So here goes. Eh? All right. So I'm going to skip this because I already talked about how the generator works. And now what I'm going to do is I'm going to talk about very large scale magnets. The United States has what's known as the high magnetic field lab. And in these laboratories, we generate the strongest magnetic fields on Earth. For example, the hybrid magnet is very strong. It is 45 Teslas. It has the world record for the strongest magnet. But let's look at the size, because that's what this talk is about. Look how much it weighs. 35 tons. How high is it? 22 feet. We gotta operate it at negative 450 degrees Fahrenheit. Okay? So, and it's been online since December 1999, and it costs $14 million. Okay?
99 million, that's a lot.
That's a lot of money. Now, remember this number. Very big magnet, very large magnet, 45 Teslas. Remember number 45 Tesla, okay? So now, let's talk about the very small, since that's what this talk is about. All right, we've talked about the macroscopic world, such as our lodestone. We can make this box even smaller to the order of 1 micrometer. Now we're dealing with the size of a cell. But I study the world even smaller than that. I live in the nano world, or I study the nano world. And what you see here is a material or a device called a quantum dot. Now, if you look very closely at this picture, we are at 10 nanometers length scales. And if you look very closely, you can actually see the plane of individual atoms. Okay? You just gotta look very closely. If you don't have good eyes, you can move up and I'll show it to you later. But you can actually see the atomic layers here. So the system that I study is just a little bit bigger than an atom. Okay? In this picture here, you're looking at an image of actual silicon atoms. Okay? Now, why? Well, okay. Let's look at the atom. If you look at the atom is the smallest unit of matter. And many of us remember learning about this in high school or in middle school, that the atom is made up of a nucleus. And inside that nucleus, you have positively charged particles called protons and particles that are electrically neutral called neutrons. Surrounded by my nucleus, I have electrons swirling around in a cloud. Now, if you want to get a sense of scale, how big this is, imagine you are watching the Bills play. All right, what do we do before we go watch the Bills play? We tailgate. We drink beer, we tailgate. Are we tailgating in the stadium? No, we're in the parking lot around the stadium. Now, let's imagine that you put a grape seed, I hate grapes that have seeds in them, in the middle of that football field. That will represent the nucleus of an atom. The electrons are going to be partying with me in that, they'll be tailgating with me. Okay? So the atom itself is made up of mostly empty space, and most of the mass is inside the nucleus of the atom. Now, just for the sake of time, how does magnetism manifest itself in nature? This is going to Christine's very deep question, what makes iron magnetic. So if you look at the electrons are swirling around the nucleus of the atom. If you have moving charged particles, you have current. And what does current create? Magnetic fields. We just saw that. So the fact that the electrons are swirling around the nucleus of the atom, that gives rise to magnetism. Okay? That's one way to create magnetism at the atomic level. Another property of an electron is that it itself is magnetic by existence. If you look at the electron contains mass. It also contains charge, but it also has a magnetic property called spin. Now, spin is something that physicists are still trying to understand at the deepest levels. If you ask me what is charge, I don't know. We just know things have charge. If you ask me why things have spin, well, they have spin because they came in existence with spin. I don't know. You know?
Born that way.
Yes, that's right. So, when you look at the iron atom has electrons that are unpaired with other electrons, giving it an overall a magnetic. What I study is not just the quantum. What you do is you replace a non-magnetic atom in the structure with a magnetic atom. That's all you do. And now you have a dilute magnetic semiconductor. Now, the system I study is quite fascinating. You can make something magnetic by shining light on it. So, how does that work? Well, it works like this. In this picture here, I have my electron in blue. I shine light, and it excites this electron. And I'm left behind the lack of electron called a hole. Electrons are magnetic, and the lack of an electron has magnetism associated with it. You have to conserve a property called, angular momentum. All right. So we have this hole. It has magnetic properties associated with it, and this hole wants to lower its energy by getting trapped in my quantum dot. So it lowers its energy by falling into the quantum dot, and I have magnetic ions in there, and my hole is a magnet, so my hole is behaving like a bar magnet on your table. The magnetic ions in my quantum dot are acting like the little iron bits in that plastic structure at your table. And what happens is there's an interaction between this hole, which is acting like that bar magnet, and the magnetic ions in that piece of plastic with all the iron in it. And they cause an alignment. Now, what's happening is at very earlier times, these magnetic ions have random configuration. Just like if you were to shake that piece of plastic at your table with the iron in it, they would have random directions. The moment that you introduce this hole in the system, or the moment that you introduce the bar magnet in that system, it causes magnetic order. Now, who remembers what magnetic field I told you to remember?
45!
45 Tesla, okay? The question is, inside my nanoparticle, how strong is the magnetic field? Well, my buddy, my brother from another mother, Vipop Barman, who does experiments at this Petro, Dr. Oswadowski in the room here, who studied the structure with me, calculated, well, they did the experiment, we do the calculation, and we found that the magnetic field depends on how big these quantum dots are. And what you find out
I
is,
thought size didn't matter.
what's that?
I thought size didn't matter.
What's that? It does. So let me get to that, Anna. So what we find is that the magnetic field strength inside my nanostructure, if the quantum dots are small, can reach 45 Tesla.
Wow.
Okay? So if you look at it, the size in a quantum dot, yes, can determine how strong the magnetic field is, but if you compare it to something like that giant magnetic structure, that giant magnet down in Tallahassee, Florida, they're getting 45 Tesla, costing $14.5 million. And they are dealing with something that are several, 20 tons, I can't remember the number. These things are nanoscale. Now, some of you are like, well, why the hell do you want to study this stuff? Right? Yes. Oh.
The question on Zoom is when you do these things like shine a light on an electron, you're actually shining light on millions of electrons, right? You can't trace a single electron.
No, so, okay, so you have many quantum dots. You're not looking at a single quantum dot in our samples. There are many quantum dots. And when you shine your light on the sample, you create a whole bunch of electrons and holes that are going to find their own quantum dots if they can find it.
So they all do the same thing. All those electrons are shining light.
Yeah, they excite them, you create a whole bunch of big population, and some of them might find a quantum dot. Some of them might get populated in 2 quantum dots. Some might get populated in 3, and so forth. Very good question. So, there's some surprise, like I just said, some of these quantum dots can be populated by more than one hole. What happens? There's some surprises. Well, if we have 2 holes in the quantum dot, we have now 2 magnets that are competing with the magnetic ions. And there tends to be ordering inside the quantum dot that looks something like this. Some of the manganese, or the magnetic ions, align with one hole, and the other manganese align with the other hole. You can also have a configuration like this, depending on how your manganese are distributed. This calculation was done by Dr. Oswodowski, 2014. He's shy. He covers his head with a helmet. But you can see here, in this blue arrow is aligning manganese around the quantum dot exterior, near the exterior of the quantum dot, and the other hole is just sitting there in the middle. Now, a recent discovery that we made in 2019 is that depending on how strong or how much energy your laser has, you can populate the quantum dot with either one hole or 2 holes. Now in this structure here, the magnetic element is hanging outside the quantum dot. So one of the holes wants to align the manganese there, and the other hole is hanging out. Well, both holes are kind of like orbiting around the exterior of the quantum. Yes?
How do you know a quantum dot's populated by more than one hole?
So it's done through photoluminescent measurements. So
You can't see it, but you can measure.
you can measure it, yeah. So depending on the color of laser light, you can populate it with a single hole or 2 holes, populate with 3 holes, and so forth. Now, why do we study this? Well, right now, if you look at your computers, you are processing information on your processor, and you're storing information elsewhere. Now, we are now making the transistors inside the chip smaller and smaller and smaller, and once you make things smaller and smaller and smaller, you have to worry about quantum mechanics. And also, we are developing a system where not only can you manipulate charge, but you can also manipulate magnetism at the same time. So you can process and store information simultaneously. That is the ultimate, one of the ultimate goals of quantum computing. So this is the end of the talk. So my talk is dedicated to my grandma who passed away in March. She was a remarkable human being, great person. My Aunt Janice came to my talk today. She's sitting over there.